In this tutorial, basically what we will see. So in this tutorial segment, basically we will see that. So today in this short video, we will discuss about some amplifiers. And second, we will discuss some loads. And third of all, we will discuss the diode connected load. And in the last, we discussed about the body effect. And channel length modulation. So this is basically the outline of today's class. So we already know that there are three types of basic amplifier configuration. If you recall that, you know you have common source amplifier, you have common drain amplifier, and you have common gate amplifier. So these three types of amplifier is available. But if you used some loads with the amplifier, then what will be the type of loads? So if you see that there are three types of load. One is resistive load. So the symbolically the resistive load seems like just a resistance. For example, this is R. This is R. And then we have diode connected load. So the diode connected load is very straightforward and very simple. Suppose you have, let's discuss the things is later. I think that should be better. So the resistive load is defined by R, for example, by the notation of this resistance. And the last we will see the current source load. So these are the three fundamentals loads for amplifiers. So initially we don't use resistive load unless we use actually the discrete component based amplifier. But our main target is actually IC design. So the size of the resistive load or a resistance is roughly 5 millimeter to 3 millimeter, for example. So inside this region, we can integrate thousands of transistors in this region. So that's why we will change our loads, and for the better performance and the higher gain, we can consider the diode connected load and the current source load. So there are other options. We can use those things. So now let us discuss about the diode connected load. So now let us discuss about the diode connected load. So if you see that for diode connected load, so there are two types of variation is actually available. So you have NMOS and you have PMOS. These two MOSFET you have. And suppose they are N channel and P channel enhancement type MOSFETs. So we know that the MOSFET has actually 4 terminals. So if we consider a n-channel enhancement type MOSFET like this, so we have 4 terminal here. So the first one is gate, this is drain, this is source, and this is the body. This is the body connection. So if you want to do the diode connection, diode connected load, you need to perform a connection. Just simply short the gate and drain togetherly, and the source will be tied to the ground. If this is the NMOS, the NMOS always will be used as a pull down network. That means your source may be tied to the ground. Unless you do this, you may face body effect. And the body effect and channel length modulation will be phase. And by default, practically we cannot neglect the channel length modulation effect because of the long channel MOSFETs impact comes from the channel length modulation. So suppose we are tied the body also the ground. That means the body and the source, these 2 terminal is short. So whenever the potential of the source voltage and the body voltage is same, that means the VSB is equals to 0 for NMOS. Whenever you face this criteria, the body effect will be not arise. Body effect is not arise. So in this case, the Vs is 0 because the source voltage is 0 volt and the body voltage is also 0 volt. For this reason, the source to body voltage is also 0 volts. So we can see that there is no body effect is arise, and if there is no body effect, the threshold voltage of the MOSFET will not change. The VTH of N will unchanged. If you change the W by L ratio of this particular MOSFET, then maybe the threshold voltage will be changed. But if you fixed a W by L ratio, for example 5, and then you consider no body effect, in this condition your threshold voltage will be unchanged. If the body effect is arise, in this case your threshold voltage will be changed. So let us see whenever we face the body effect. So let's try to see whenever we face the body effect. So after going to the body effect of NMOS, let us see the PMOS with no body effect. So PMOS, that connected load. So for PMOS diode connected load, this is your PMOS, this is your VDD suppose, this is your drain, this is your gate, and this is your source. The rule of thumb is same, that is the gate and drain will be short togetherly, and if you do this, you can get a diode connected load by using the P channel MOSFET. And here also you have a terminal like body, so the VB should be VDD in this case, and the Vs is also VDD. So for the PMOS, the VSB should be is equals to VDD. If this criteria is maintained, in this case, let us connect the body terminal with the VDD. In this case, you cannot face any body effect. So body effect is actually not changing. There is no body effect. For a particular W by L ratio, Suppose you have 5 and your body effect is not affected by your MOSFET. So in this case, your threshold voltage of the PMOS will be unchanged. The threshold voltage of the PMOS will be unchanged. So this is the fundamental introduction of the diode connected load with body effect. Now let us discuss about, this is without body effect. Without body effect. So this is without body effect. Body effect. Now suppose we consider with body effect, then what will happen? So if you consider the body effect with PMOS, for example NMOS at first. So let's say your VDD is now here. So this is your VDD, and then you have a N-channel enhancement type MOSFET. So again, this is your gate, this is your drain, and this is your source. And after the source, you have a circuitry here. For example, a single MOSFET or a circuitry here, and then you ground it. So this is your body terminal. You always know that the body terminal will always tied to the ground for NMOS. This is NMOS. So your body terminal is tied to the ground, and this is your source terminal. If you see that, this is your source terminal, and if you connected the gate and drain togetherly, this MOSFET will act as a diode connected load. So now question is that how do you phase the body effect for this NMOS? So you see that the VB is equals to 0 voltage because your body is directly tied to the ground, but your source is directly not tied to the ground. There is a circuitry here. So for this reason, your Vs is not is equals to 0 voltage. So your source to body voltage is not is equals to 0 voltage. So in this case, you phase body effect. You phase body effect, and the impact of the body effect will be change your NMOS threshold voltage. So the threshold voltage of this NMOS, because we talk about for the NMOS, so the threshold voltage of this NMOS will be increased a little bit higher. Increased a little bit higher during the body effect. Similarly, we can consider for PMOS also. Suppose you have VDD here, and then you have a circuitry. Suppose you have a circuitry in the pull-up network, and pull-down network you have a PMOS. Pull-down network you have a PMOS, and this is your gate, this is your source, and this is your drain. So whenever you connect the gate and drain togetherly, it will act as a diode connected load. So now you can see that your source VB suppose tied to the VDD. So this is your body. So body is tied to the VDD. So you can write that the VB is equals to VDD voltage. Let me just clean. Your VB is the VDD voltage, and the source is not directly connected to the VDD because there is a circuitry. So Vs is not is equals to VDD. That's why your VSB is not is equals to VDD. For this reason, you will face body effects. You will face body effect. And during the facing of the body effect, your threshold voltage of this PMOS will increase. So this is happening for the body effect. You can observe if the body effect is considerable or not considerable. So by based on you actually find out those things. So now let us consider a very interesting term, that is how to we will find out the output resistance for the diode connected load. So output resistance for diode connected load. So suppose we have a n-channel enhancement type MOSFET, and the source is tied to the ground and body and source are short togetherly. So this is your drain, this is your gate, and the gate and drain will be shorted togetherly. So the question is very straightforward and very simple. That is, whenever you will look at from the drain side, how much resistance you actually feel, that is your output resistance. You need to be look up, or you need to be see from the drain side, this side, how much resistance you will be face. So to the small signal analysis, I actually skip these things here. You can find out by the derivation of analysis, small signal model. This MOSFET can be replaced by using two resistance. So R out is will be 1 by GM parallel RO. So this is the output resistance, and this will consider whenever the lambda is not is equals to 0, that is the channel length modulation is considerable. At that case the RO is finite, and RO is basically nothing but 1 by lambda ID. 1 by lambda ID. So you see that you consider here the channel length modulation, that's why your R out is look like this. So how to we can write this? So let us break down this MOSFET in terms of like two resistance. You will face like this type of two resistance parallelly and then ground it, and you look from here. So this is your R out. So this is your drain, for example. This is your source, and your gate and drain is actually short. So you face that is this resistance is 1 by GM, and this is RO. So 1 by GM parallel RO. And similarly for PMOS, you also get the same things. You get also same things. But whenever the lambda is equals to 0, that means if you see that, you see that the R0 is also 0 or ignored. You can ignore the R0. In this case, the output resistance will be just simply 1 by GM. So that's how we find out the output resistance of a diode connected load for NMOS. And similarly, we get this value for the PMOS. If I describe this scenario here in a little bit, this is your VDD and this is your PMOS, and this is your gate, this is your drain. So the gate and drain will be short. We will see the output resistance from the drain side. You face, if you consider the channel length modulation, it will be 1 by GM, parallel arrow. And if you not face any channel length modulation, in this case, your R out should be is equals to 1 by GM. All right. So whenever you consider the channel length modulation, one term will be additionally more here. That is this GM plus GMB. And whenever you have just without any channel length modulation, you have just GM parallel arrow. GM 1 by GM. Sorry, this is my mistake. This will be just 1 by GM. Nothing else here. But whenever you have channel length modulation, in this case your arrow is finite, so 1 by GM plus GMB parallel arrow. So this is your output resistance. And for the PMOS, you consider the channel length modulation. So you also write here GM plus GMB and then parallel with arrow. And the R out is simply 1 by GM. So I think this tutorial is useful and very helpful for students. And with this, I conclude the tutorial segments. So thank you.